We made a great decision in this country to invest in our future by building the interstate system. And the economy boomed as a result of that. How do we maintain that system? How do we expand that system?
Our infrastructure is incredibly important. It's what carries us to work, is what we rely upon to move goods and to move us from one place to the other. It's allowed us to see from coast to coast, the beauty of America. We've invested in that over the years, and here we are essentially 60 to 80 years after we've built this infrastructure, and we need to take care of it.
In the United States, there's roughly 600,000 bridges. The U.S. spends roughly $5 billion per year on bridge deck deterioration. But if you look at the total cost of those bridge assets, it's north of $2 trillion. So $5 billion might sound like a lot, but it's less than 1% of the total cost of those assets.
Well, a large percent of bridges in this country are either functionally obsolete or structurally deficient. And the question is, how do you prioritize? Which do you act on first? You can't shut them all down at one time.
Public enemy number one when it comes to preservation of bridges is really uncertainty. And we don't fully understand why bridges deteriorate. Until we figure that out, we don't know how effectively to spend our dollars to prolong the life.
And what the BEAST will allow us to do is to look at the materials we're using and make smart decisions about how we build our new bridges, how we take care of the bridges that are here, and how we move forward with that important infrastructure.
This facility was basically created as a result of the feedback that we received from the stakeholders of the long-term bridge performance program.
One of the drivers for the BEAST is actually the states coming to the Federal Highway Administration and researchers in general and saying, we want a more scientific means of studying deterioration and ultimately how to preserve these bridges.
There are a lot of questions that would require years and years of monitoring our bridge inventory to be able to answer them.
Bridges are durable. If you build a bridge today, it will be 20 to 30 years until you start to see deterioration. And so it makes deterioration very difficult to study.
The question is, can we wait 20, 30, 40, 50, or 100 years to do an analysis?
The key is to condense that time. So in, say, 10-month time period, we can study 15 to 20 to 30 years of deterioration. And that's really the primary benefit of the BEAST.
The BEAST facility will allow us to take a look at full-scale samples. And when we say full-scale samples, we're talking about a 50-foot span, 28-foot wide, with a depth up to 5 feet. A bridge that would resemble what's in our inventory. We would open up the BEAST so that we could lower and install the bridge inside the environmental chamber.
The bridge itself has, all of the primary bridge components.
Once that bridge is installed, we close the BEAST, we close the environmental chamber, and we can begin the test.
There is a very large rear carriage of a tractor trailer that can impose 60,000 pounds of vertical force and roll back and forth at 20 miles an hour.
Which gives us about 17,500 passes per day. As we're doing that, we'll be able to begin a cycle of heating and freezing, bringing the temperatures all the way up to 104 degrees and maintaining that temperature for a certain period of time. Then we'll bring it back to ambient temperature, and then from that point, go down to 0 degrees for another period of time.
You can cause it to rain and precipitate in there. You can apply de-icing chemicals just as they would be applied out in the field. So you get all of your primary inputs, your maintenance activities, your environmental temperature changes, precipitation, and you get the live load.
By doing that heating and cycling, what we're anticipating is that we'll be able to age that bridge by 15 years in a matter of 6 months.
We will be performing visual inspections, which is how bridges out in the field are assessed. So we'll be able to correlate what happens in this accelerated environment with what happens out in real life.
By being able to put a standard bridge deck in the beast and test it under these conditions, you eliminate those variables of size and scale that are very difficult to match in a lab environment by being able to do everything with actual bridges.
We would like to look at it holistically. We would like to take a look at the entire bridge and see that as a whole it's a complex phenomenon.
So the two key things that the BEAST provides are, one, it provides researchers with the ability to control the inputs into the structure. So those are environmental inputs, maintenance inputs, and truck and live load inputs. So for the first time we can control this at a full scale. So full scale bridge, and we can control these types of inputs. The second, and arguably more important thing, is it allows researchers to condense time. Nobody has this ability to shrink time, to accelerate the deterioration process, to provide a scientific approach to studying these problems. And so our last resort was, well, we're going to have to build one then. And that's exactly what Rutgers did.
To design a laboratory, a facility that can do something that's not being done anywhere else in the world certainly felt like a big challenge.
This was a combination of environmental control, load control, and sheer physical size that, the team was pretty excited about it when we were proposing, and then obviously when we won the job, nervous about it. How are we actually going to pull this off?
It felt like we were taking a leap into futuristic research.
The beast was a challenge. It's over 120 feet long, about 20 feet high, and several 100,000 pounds. We got to put that all together in our shop and then figure out a way to get it out of the shop. We basically ended up having to cut holes in the wall in order to get the beast out when we were done with it. Once we had it out the door, it took 17 tractor trailer loads, including oversized loads, because the beams are one piece, so 120-foot long trailer going from central Vermont onto the interstate and then down to New Jersey. Things came together and we were able to get it down here and put together. It was very fulfilling to get it done and see it work here on site.
Applied Research Associate contributed tremendously to the creation of the facility, and also we plan to work with them closely in the future in the design of the experiments.
The folks associated with putting the beast together, the fellows down here at CAIT and Rutgers and ARA, we were all in the boat together. And we just kind of brainstormed a number of ideas and ended up coming up with what we ended up building.
The creation of this facility could not have been accomplished without the help of a large number of individuals and organizations. New Jersey Department of Transportation, the Bureau of Research, the Transportation Committee of the New Jersey Assembly. Assemblyman John Wisniewski, who heads the committee, was very helpful in the process. The Federal Highway Administration's Division Office in Trenton, the School of Engineering at Rutgers University, and the staff and co-workers at the Center for Advanced Infrastructure and Transportation dedicated their time and put a lot of effort in making this facility a reality. We also presented this facility as an opportunity where we could essentially turn this facility into a national laboratory.
What we don't have now is industries coming out with new materials, new approaches to build better bridge decks, to preserve bridge decks. And one of the reasons is that feedback loop of 30 years is just not compatible with a business cycle.
So the beast really is a test bed for new materials to be brought in and to be validated. They'll be able to actually work towards beating the beast, coming up with ways in which the bridge will outlast all of the environmental loading, all of the physical loading, all of the beating that the beast will provide.
When we do analysis with tools like the beast, I can see departments of transportation modifying their approach, and being more accepting of new materials. I think there's a lot more comfort in that when they can see data that proves their point.
Once we know how the original bridges deteriorate, how the patching material ages, we'll then be able to take a look at new materials and build 21st century bridges that do last 100 years and beyond.
Just like you would invest into oil changes and different tune-ups on a vehicle to keep that vehicle operating long-term, we should be doing the same for our bridges. You know, you're going to spend this enormous amount of money on bridge preservation. Let's take 1/100th of 1% of that, and let's make sure that we're spending it in the most effective way.
So seeing it come together, seeing all the components on site here at Rutgers University, the feeling was that we're ready. We're ready to begin work. We're ready to start these experiments. We're ready for researchers to come and talk to us and collaborate so that we could come up with these answers that will help our infrastructure move forward.